Hello, everybody, new friends and old friends. Now, we live in the marvelous times where machines are solving our problems, inspecting our sensors, parking our ships, granting our loan applications, and whatnot. I don't have to convince you of this, right? You're at this conference, so you already know this. But what I think is most interesting is when machines manage to solve problems that we cannot solve ourselves, or when we don't know what it is machines have learned. Now, I think that the first time the general public, not just us IT nerds, realized that machines can actually outperform us in thinking was in 96 and 97, the first time a machine, Deep Blue, beat a chess grand champion. That was, or grandmaster, sorry, that was Garry Kasparov, and he was not happy about that, to put it mildly. And I can sort of empathize with that, because what happened was not strictly speaking that Kasparov was beaten by a machine, right? He was beaten by an engineer who had a tool that could search through possible future board positions much more efficiently than Kasparov's brain could. Now, on the other hand, we are getting machines that can learn themselves to play chess without our help, without us telling them about chess, and who beat not only our human chess masters, but also Stockfish and Deep Blue. Today's chess masters are machine learning models, and even kind of Kasparov has come around a bit and said that what these machines do is truly remarkable, because they can actually teach us something about the game of chess itself. So he says that we can actually learn something from the new knowledge that these machines produce. And while I kind of get what he's coming at, I understand what he means, I'm also like, can you really though? Can you really learn something from these machines? Because, okay, so the way I picture a match between a grandmaster in chess, like Magnus Carlsen, and the machine is something like this. Like they're having the time of their lives, and they go like, oh my god, machine, you're so good at chess. And then, of course, it doesn't actually look like this, but it's difficult to find illustrations of these chess engines. And then after a match where Magnus Carlsen has been beaten by AlphaZero for the gazillionth time, or maybe during a match where AlphaZero makes a brilliant move, maybe Magnus Carlsen goes something like, okay, machine, why did you make that move? I don't understand it. I wouldn't have made that move. And the machine goes, awkward silence, right? Because these machines were made to play chess, not to teach us about chess. So what can Magnus do then? Well, he can definitely stare at the machine, because there's no secret. I mean, he can go on GitHub and check out the source code of AlphaZero, and also the trained neural network with all its parameters. So the AlphaZero is definitely both traceable and transparent, but what Magnus Carlsen would see then is something like this. He would see 20 so-called residual blocks of fantasillion parameters, and they all have the numbers, and then he could learn something from the engineers that made AlphaZero about how it was trained by self-play and the batches and everything. But Magnus wouldn't really learn anything about chess and why AlphaZero makes the moves that it makes from this, right? So here we need to learn some terminology, because AlphaZero is traceable, right? Everybody can go and look into the operations that AlphaZero performs, and they're not a secret. That's not enough to understand AlphaZero. What AlphaZero is not, and this AlphaZero has in common with most large machine learning models out there, it's not interpretable, right? Because interpretability refers to a passive characteristic of a model, referring to the level at which it makes sense to human, right? If something is interpretable, a human can look at it and go, yeah, all right, I see. You could do that with like Newton's second law. Right, you go like, okay, force, mass, acceleration, okay, I see. That's not what this is about either, okay? Explainability is an active characteristic model that, an active characteristic of a model that it needs to get afterwards, because it is traceable but not interpretable to humans. So explainability is about taking a model and performing an action so that humans can gain understanding of the model. So the most important concept in explainable AI, in XAI, is understandability. And there are at least 2 conceptual steps to this, because in order to achieve explainability or an understanding of a model, first you have to make an accurate proxy of the model. You have to extract the relevant information for the understanding, for the explanation, and then you have to formulate the explanation in such a way that it makes sense to whichever human receives it. Okay, so there are 2 separate steps. And one method can definitely address both those steps, but we have to kind of keep in mind there's 2 things. There's the machine part and kind of the human part. All right, now why is this difficult? Well, today's machine learning models are programs that learn from data, which you could, I guess, call experience. And intuitively, I really think about machine learning as artificial intuition. And something you have intuition for, like walking, like how would you explain to somebody how you walk? It's actually pretty difficult, right? So it's a difficult task to explain something that is learned from data or from experience from the get-go. Secondly, the way that machine learning models solve problems that we give them is by transforming data to high-dimensional spaces corresponding to their internal layers in a non-linear way and exploiting complex relations in the data, meaning putting together information from several of the data pieces. Now, when we humans want an explanation, what we want is a simple story about the world. We don't want non-linearity because we're bad at that, and we don't want complexity, right? So you could actually say that what machine learning models do and what we want from explanations are complete opposites. Okay, so that is a huge challenge. And I kind of just want to stress a bit here that this is not because machine learning models are like bad and don't want to or anything. It's because they are the result of this thing called predictive modeling. And that is something else than explainable modeling. Now, explainable modeling, that is what we do when we try to understand like the world around us, like when we derive Newton's second law and stuff like that. We want to explain the underlying phenomena. When we do predictive modeling, it's because we've kind of given up a bit on that, or when we've said that's too resource demanding, we're not going to do that, right? We just want to do forecasting. I have data, I want to know what's going to happen. Okay, so we've kind of already abandoned explainability. That wasn't the goal from the beginning. Secondly, unfortunately, I kind of have to say here as an honest researcher that you cannot test your way to understanding a large machine learning model. You just cannot. That's because of the curse of dimensionality. Don't have time to explain that now, but Google it if it doesn't scare you already. But it's this property of our universe that some tasks get more difficult only because you increase the dimensionality of the problem. This here is my favorite example to kind of scare people with the curse of dimensionality, because it was shown some 3-4 years ago that the kind of road sign recognition models that are used in cars, such as Teslas, can be fooled with the right sticker combinations on, for example, a stop sign to make the model believe that it's a speed limit sign. Now, the point is not that you can't correct these things in the machine learning models once you found them. The point is that none of you would ever have thought of checking for exactly that pattern, right? So the search space would be too large. You cannot test your way to understanding where a model's faults are. And this is a problem that we know from security and from cybersecurity. You can't test your way to everything that's going to happen. You need to understand. Thirdly, if you dig a bit into XAI, you're going to find a gazillion methods that all promise different things. That does not mean that the field is very mature and nice, okay? That actually means the complete opposite. It means that there are very many different approaches, methods, but no solutions that solve all cases. There are no unifying principles or benchmarks, and between the methods, there isn't even an overlay. The methods don't kind of transition smoothly into each other. There is no agreement regarding what a good explanation is or when an explanation has been given. Also, perhaps different end users require different explanations, so this might even be an unsolvable problem. But what we can do, instead of trying to dive into all the different XAI methods out there, we can take a step back and go, okay, but conceptually here, what can go on? And actually, I would say only 3 things can go on. Now picture God gives you a black box, a machine learning model, and you want to understand, as a scientist, what it does. Now you can do three things, right? What you can do, you can poke the system systematically from the outside and observe how the behavior changes. And based on that, you can say something about how it will probably behave in the future. What you can also do is you can take a system that behaves similarly in certain occasions and say that, well, okay, so around these occasions where the two systems behave similarly, I guess they have the same kind of working mechanisms. So then you can take a familiar system that behaves similarly and say that, okay, I guess these work more or less the same way here in this neighborhood. Or you can get all frustrated, take a big hammer and smash the box and look what's inside. Right? Those are the three approaches. And because I've talked so much and have so much time left, we're actually going to go through the most popular methods that you can just download and install on your computer and test within each of these categories. All right, so let's start with the extrinsic explanations. The most popular form of extrinsic explanations are the so-called feature importance rankings. Sorry, that slide is a bit messed up. What you get then is a list of all the features that the model receives, ranked after importance. I stole this plot here from my days at PwC, where we made a cabin pricing model, and of course the end user wanted explained why this price came out for the cabin. And as you can see there, the most important characteristic of this cabin was that it's located in Trysil. And I think that one of the reasons that we humans like explanations such as these is that we can interpret our whole worldview into this. Because if I say, this is an important cabin because it's located in Trysil, you all go like, yeah, Trysil is like a chic area, I know a way to have a cabin. But if I said that this cabin is kind of cheap because it's located in Trysil, you'll go like, yeah, obviously, noisy place, right? You would rather go for Hardangervidda or something. So I think that this feature importance ranking really appeals to us humans, because we can just interpret kind of our own worldview and logic into it. Now, this ranking here was made with a package called SHAP. SHAP is, I think, about as close as you can get to an industry standard in XAI. So kind of remember the name, okay? If you have heard about one XAI method, chances are you're going to stumble across SHAP at some point. SHAP is based on this jewel from cooperative game theory, absolutely marvelous, called the Shapley value. Lloyd Shapley introduced it in the 1950s, and he received the Nobel Prize in Economics for it in 2012. And unfortunately, I cannot give you all the details, but if you want, you can take a picture of the slide, and I'm going to share it afterwards also. This explains how you can use the Shapley value to fairly and uniquely divide any taxi bill among me, yourself, and a third friend if we go out on town tonight. And one thing that I just really want to make you aware of, which I think is kind of intuitively really nice about this, is that if we in total, we go different distances, but in total we go 10 kilometers, the fair way to divide this taxi bill here among us would be that the first one who goes 3 kilometers pays for 1 kilometer, the second one who goes 7 kilometers pays for 3 kilometers, and the last one who goes 10 kilometers pays for 6 kilometers. You see, all of us pay less than we would have had to do if we had gone alone, because cooperation is nice. And you see that 1 plus 3 plus 6 adds to 10, so the total cost is divided. This is a result of the axioms of the Shapley value, which are really kind of a really strong fundament for an explanation method. I think that's why the SHAP has become so very popular. So go home, write pip install SHAP into your terminal, and go and play around with SHAP. Next, surrogate model explanations. I think the best way to get an intuition for how these models work is the way that I can say that the Earth here locally where I am is flat. If I want to model here a phenomena that happened on this floor, I can just say, I don't need to use curved geometry, this here is flat. That's exactly what you would do if you want to explain a complex machine learning model with a simple model in a little neighborhood. There is also a package out there that can do it for you. It's abbreviated LIME, locally interpretable model agnostic explanations, and you don't have to use a straight line. The surrogate or explanatory model can be a decision tree. It's basically your choice, and what LIME does is that, I'm going to say the ugliest words I'm going to say today, what it does is it minimizes the loss between the complex model, the full model that you want to explain, and your explainer model, while minimizing the complexity of the explainer model. Marvelous, right? All you need, fantastic. So go write pip install LIME in your terminal, and you can play around with this one also. Finally, the intrinsic explanations, that thing where you smash the box and look inside. Most of you have probably seen these pictures. We ask, why did the machine make this decision? Part of the picture lights up, and that means that these pixels were important for the decision. These are called activation maps. The most popular library for producing them these days is called GradCam. The thing about grad is gradients. So what is the gradient of the resulting class that the black box model or the full model predicts for an image when you change the pixels? If you change a group of pixels and the decision changes a lot, then you know that those pixels were very important for the decision. All right, however, beware, there are very many of these activation map libraries out there, and this paper called sanity checks for saliency maps. If you want to become an expert or a frequent user of saliency maps, you should check out this paper because it shows that you can actually cascade randomness through a neural network, and the saliency map that's supposed to explain the neural network kind of barely changes, which I think reveals to us that many of these methods only do edge detection, which we learned about earlier today. So finally, back to this marvelous guy who said that we can actually learn from the new knowledge that machines produce. He called chess Drosophila of reasoning, and Drosophila is just a fruit fly for fancy people. And I do agree with that, because already in the 90s, kind of, it was already very impressive that a computer could beat a grandmaster in chess, but now we see that AlphaZero is kind of, I think, opening up the future paths for the field of XAI, because what a team from DeepMind, together with another chess grandmaster, Radimir Kramnik, have managed to do is that they've seen how human chess concepts propagate through a neural network. So the chess master said, these are the important board positions for me as a chess player to look for, and they've identified those concepts inside AlphaZero. Absolutely marvelous. That, I think, is part of the future. The other step in the glorious future that I think all of us are going to notice is that XAI is going to split up into two parts. A technical part and a kind of a communication part. And I see the clock is ticking, so I'm not going to elaborate more on this. What I think is going to be a huge problem, though, in XAI, and something that I don't even I research this 120% of my time, and I absolutely dig it, but I don't know if we're going to be able to overcome this challenge, is that machines might or are probably modeling non-human concepts. If you've heard of AlphaFold, that's a machine that more or less solved protein folding. Now, we had no idea how it did it, and it just absolutely outperforms all humans and non-machine learning computers on the planet. And this has been one of the holy grails in microbiology, and we don't know how it does it. Maybe AlphaFold has modeled a concept that we just kind of don't have. Maybe it's found a little law of nature that we just don't know. How will we get the machines to communicate that to us? I have absolutely no idea. So I'm very happy that I have research funding. Yes. Thank you so very much for listening to me, and questions?
Take a deep breath, because I don't think you actually took your breath at all during these 20
No, I don't breathe, I drink coffee.
Yeah. I noticed. Very good. Well, this is mind-blowing, Inga. I guess you have fun days at the office.
I do, yeah.
I can imagine.
Sometimes I cry.
So, there are some questions.
Nice.
Can the prevalence of explainable AI make it harder to justify using a more accurate but non-explainable AI?
Yeah, okay, so there is this thing out there that people call the accuracy interpretability trade-off. And I can sort of, when we talk about predictive modeling, yes, I buy into that. The more complex you make a model, the more accurate it's probably going to be, and the more difficult it's going to be to stare at it and understand what it does. Now, this does not mean that no interpretable models can be accurate, okay? Newton's second law, 3 symbols, F equals ma, that's interpretable, and it's marvelously accurate, right? So this isn't a law of nature, right? It's a trade-off that we've done to ourselves because we're bad at statistical modeling. Also, it's not an accuracy explainability trade-off. No. Explainability is something that you use afterwards when the model is done and you say, I want to explain it. Of course, you can develop the explainability method as you develop the model itself, right? But explainability and interpretability are not the same thing. Not saying that the question asker thinks that.
Thank you. So I'm going to continue. Well, no, actually, because you said you would like to dwell a little bit about the development of explainable AI between the technical and the more psychological side of things, which is really triggering me, of course, as an end user. Where are we seeing that development? Are these going to be 2 parallel tracks, or is one going to be more important than the other?
Oh, that's really interesting. And I think that's just up to us, where we kind of choose to put our efforts and what kind of research is funded, and of course also what the tech giants notice is
required.
And most important, just to be accepted, right? Is it that their developers understand their models and can make them more robust, or is it that the public will accept the models? It's difficult to say. What I do hope, though, is that it's not going to become a divide in communities, so that no techies want to talk about kind of communicating and no people focusing on communicating explanations to humans try to understand what the technical methods are about. Right? I mean, probably it's going to happen because as humans, we like to kind of dig into our small little favorite topics, but I do hope that the field is going to divide kind of only in types of publications, not in mentalities. And also one thing I want to add there is that the better we make machines at explaining themselves, the better we will make them at justifying themselves. And explaining and justifying are 2 different things. And I kind of don't want to go into a future where machines are just excellent at justifying bad decisions. Right, so that's also something that I think that we need the social scientists and the philosophers for, because we techies can get a bit blind.
Yeah, well, I guess you're not the only ones, actually, in that. And that is also something we could discuss later on, so keep that thought. Can the fact that much of AI is non-explainable also be an advantage?
Well, I'm a particle physicist, right? I'm like, how does the universe work? What we humans have been doing since we crawled out of the soup, and the primordial soup, and climbed down from the trees was understanding what's going on, right? So I don't see a benefit in not understanding something. I mean, things have always improved as we've understood more, but there is definitely a discussion out there regarding, is this misplaced effort? No idea, but I mean, my personal answer is absolutely no. No, there's no benefit in not understanding.
What's the limitations of SHAP?
There are many. How technical do you want me to go? I have 2 minutes. Okay, a main limitation is really that. Sorry for those who don't like my words right now, scroll on Instagram or something. A main limitation is that when you want to calculate Shapley value, what you have to do is that you have to remove players from the game and see how the game plays out then. For a trained machine learning model, you can't just remove features, right? You're going to get a PyTorch or a TensorFlow error saying shape mismatch. Okay, so the way that you remove features, or the way that SHAP removes features from a model, is by simulating feature absence, by calculating expected values from model outputs. Now, when you remove a player from a game, you do a causal intervention. You can't do a causal intervention on an existing data set. So that's a huge weakness. You pretend like you're intervening on a system when you're not actually. And also this calculation of estimation of a model output relies always on assumptions, and very many people who use SHAP don't know what those assumptions are. So what you're doing is that you have a black box and you put another black box on top of it and go, woo, explained. Was that?
Judged by the reactions, yes.
Thank you.
Very good. So, question for some comments from you. Someone, I don't know who, but someone, some people might argue that models such as AlphaZero or DALL-E 2, does that ring a bell? DALLE 2.
No, but I should probably have heard of it.
Yeah. Are so complex that they cannot be explained in a way understandable to humans. Comments?
Yeah, we thought that about black holes and elementary particles also. Don't give up so easily. You know? It's a big adventure. Go out there, understand things. Don't be discouraged. It's just numbers.
So this is following up the same remark. Human decisions are arguably also unexplainable. Well, yeah.
Yeah, good thing humans aren't the standard.
Yeah. We are good in making up explanations that make sense, but are not necessarily true.
Yeah, justification instead of explanation. We should definitely hold machines to a higher standard than humans.
Yeah.
Yeah. Good last word?
This is an off topic, so we're going to finish with that since we're already over time. Have you watched a lot of 2-minute papers? That Absolutely Glorious was perfectly delivered.
Oh, thank you.
Yeah, well, it was not for me. I'm just the messenger. So, in the spur of the moment, I forgot to bring the book that you're going to get. But you're sitting right next to me, so you're going to get the machines behaving badly afterwards. And Inga is going to be back for the panel discussion this afternoon. Probably she is going to be doing all the talking together with a couple of the others in the panel. So we're looking forward to that. Thank you so much, Inga Strümke.
Thank you, guys. Thank you.